So we have something like pH versus volume added, right? And so then you've got something that maybe does this, right? So let's assume that this is a weak acid and a strong base titration. Is that what we want to do? Let's do it the other way around. Let's say weak base, strong acid concentration. All right, so let's assume something like 0.5 molar NH3, and let's titrate it with what? 0.1 molar HCl. Weak base, strong acid. So can we calculate what is the initial pH of the solution? That's right. So we know that pH is equal to minus the log of the H3O plus concentration. So now we just need to find what's the H3O plus concentration, right? Well, how are we going to get that? Yeah, so take a look at our graph over here. We're starting out with base and not acid, right? We're starting out with pH greater than 7. So if we were starting with the HCl, then our pH would be 1 because it would be negative log of 0.1. But we're starting with the base, and so we need to calculate from the base what is our concentration of H3O plus. In order to do that, we need an ice table. Okay. So let's write the reaction out. This is a base, so we need the base ionization reaction. So the base ionization reaction says that our NH3 will react with water, and that will establish an equilibrium with NH4 plus OH minus. Okay. Because this is the initial concentration. We haven't added any acid yet. So now we'll do the ice table. So initial conditions here will be 0.5 molar of this, and 0 of this, and 0 of this, and the water doesn't matter. So now change will be minus X here, plus X here, and plus X here. And then the sum of those will be equilibrium. And so that'll be here 0.5 minus X, and X, and X. And the equilibrium constant for this thing, the Ka, is equal to what? Concentration of NH4 plus times the concentration of OH minus. It is Kb over the concentration of NH3. So we can throw in our equilibrium row, and we'll get X squared here over 0.5 minus X. This requires a quadratic formula to solve. So let's make the assumption so we don't have to have the quadratic formula to solve it, right? So let's go ahead and say that, can I change my color here? Yeah. Let's say that this is very small, so that 0.5 minus x, why is it doing that? Stop that. So we can say that 0.5 minus x is approximately equal to 0.5. All right. So then our KB equation over here becomes x squared over 0.5, which makes it easier to solve for x. All right, so what we need is we need the value for KB. So we need to look up what is the KB for ammonia. So we can Google that real quick. Absolutely. I'll take it. All right, so now we just got to solve for x. So we multiply by 0.5 and take the square root. So 1.8 times 10 to the minus 5 multiplied by 0.5, and all of that, take the square root. .003. All right. So what does that number tell us? That's right. And what concentration do I actually need? Yeah, well, I need H3O plus, right? Okay, I like that. I like that. So let's do that, right? So this is equal to the OH minus concentration. So calculate POH. POH is going to be minus log of the OH minus concentration. POH is 2.5. All right, so how do we get pH? Okay. So we get 11.5 is the pH. So that means that this value up here is 11.5. All right, so now let's pick another value. So let's pick another point on this thing. So maybe, first of all, we need to establish some volume of this stuff. So let's say 50 milliliters of this stuff is what we're going to start with over here, of our ammonia, all right? And now let's pick a couple points and just calculate here. So let's say, let's pick the point here where we've added, say, 20 milliliters of acid. And let's pick 60 milliliters of acid. And let's see what happens, right? So the first thing we need to do is figure out how many moles of ammonia are present, right? Because anytime we do these calculations, we have to know, are we going to be before the equivalence point, at the equivalence point, or after the equivalence point? And the way we do that is we compare the number of moles. So let's calculate the number of moles of ammonia initially here. So the number of moles of NH3 is going to be equal to, we said 50 milliliters, right? So 50 times 10 to the minus 3 liters multiplied by 0.5 moles per liter, because that was our concentration. So that's going to give us some number of moles. .025 moles. Good. All right, so now let's calculate the number of moles of HCl. At the 20 milliliters would be the best place to start. So we say here 20 milliliters. So that's 20 times 10 to the minus 3 liters. Multiplied by, what's our concentration? 0.1 molar. So how many moles of HCl here? So we are before the equivalence point. So anytime that we're before the equivalence point, we have a buffered system, right? So how do we calculate the pH of a buffered system? Gotcha. So the pH of a buffer is given by the Henderson-Hasselbalch equation. So pH is going to be equal to the pKa plus the log of the concentration of the base over the acid. So we know how much base, we know how much acid. Now we need a pKa. We got a pKb. Do we know a relationship between? Well, we know this. We know that Ka times Kb equals K water. Or if we take the negative log of both sides of this thing, we get pKa plus pKb has to equal 14. But let's go ahead and calculate Ka, right? Because we have Kb written directly up there, right? So Ka will be equal to K water divided by Kb. And so my Ka will be equal to 1 times 10 to the minus 14, that's K water, divided by 1.8 times 10 to the minus 5. So what will my Ka be? .55 times 10 to the minus 9, or 5.5 times 10 to the minus 10. All right, so now what's the pKa? Good. What's up, man? All right, so we got a pKa of 9.26, so we should be able to throw that in. Brady, what we're doing is she asked about a titration. We're doing a weak acid, strong base titration. And we are using 50 milliliters of half molar ammonia solution, and we're titrating it with 0.1 molar HCl. And what we've done so far is we've calculated the initial pH of the system, and right now we're working at what is the pH after we add 20 milliliters of acid. And so we talked about while we're in this region before the equivalence point, because we've got a weak acid and strong base, weak base and strong acid, we are in a buffered region. And so we can use the Henderson-Hasselbalch equation to calculate the pH. So now we can throw those values in. So we can say here that our pH is going to be equal to our pKa, which is 9.26, plus the log of, now our concentration of base is going to be 0.025 divided by 0.002. That's our acid. Now, I know I just used numbers of moles there. I didn't use concentrations. Because they're in the same container, they have the same volume, so their liters would cancel out in both cases, right? You could calculate the molarity here. You could divide each one of these things by, 70 milliliters, right? And you get two different molarities. Because we had 50 milliliters of NH3 and 20 milliliters of HCl. But I'm telling you, if you write out 0.025 molars divided by 70 milliliters and 0.002 mole divided by 70 milliliters, the 70 milliliters cancel. Right. All right, so now we need to calculate that log. What is the log of 0.025 divided by 0.002? So that means our pH of the system at this point is going to be 10.37? Gotcha. So now let's do the same thing for 60 milliliters. All right. So let's find the number of moles of HCl at 60 milliliters. So that's going to be 60 times 10 to the minus 3 liters, 60 milliliters. And we're multiplying by the concentration of the HCl, which we said was going to be 0.1 moles per liter. And so we get some number of moles here. 0.006. Have I reached my equivalence point yet? No. So if I haven't made the equivalence point, the calculation works exactly the same as the previous, right? We're still a buffered system, so it's still going to be pH is equal to pKa plus the log of the concentration of the base over the acid. So this is still going to be 9.26 plus the log of, in this case, 0.025 divided by 0.006. Should be lower than 10.36, but not by a ton because we're in a buffered system. .88. All right, let's see here. So now let's say we've added, instead of 60, let's say we've added, hey, what's up? 250 milliliters of HCl. So now we're going back up here to our thing. So this is kind of pour here. So maybe 60 is right here. And now we want to go to 250, okay? So let's calculate the number of moles of HCl at 250 milliliters. So it's going to be 250 times 10 to the minus 3 liters, multiplied by 0.1 moles per liter. And how many moles is that? That's the same number of moles as the base that I started with up here. Right? Here's my moles of base. So this is the equivalence point, right? This is defined as the equivalence point. So what that means is that we've converted all of our base into the conjugate acid at this point, right? And we know that because this value is the same as the value of the NH3 we started with. So now this means that all NH3 has been converted to NH4 plus. But we also know it's not going to stay like that. NH4 plus is the conjugate acid of a weak base. So it can react just like an acid reacts. So it can do the following. We can have NH4 plus H2O establish an equilibrium with NH3. And what's the other product? H3O plus. This is a Ka equation, right? This is acid plus water gives me conjugate base and H3O plus. So there's a Ka associated with this equation. Well, we know that Ka. We calculated that Ka already. What is that Ka? There you go. I gotta see if I can turn that heater off because it's like 1,000 degrees in here. Okay, so now that we have created our Ka equation, can we use the Ka equation to calculate the pH? So we have this equation here, and we know that in this case that the Ka is going to be equal to the concentration of H3O plus times the concentration of NH3 divided by the concentration of NH4 plus. And so if we can write an ice table for this thing, then we can solve for the H3O plus concentration. So we'll build the ice table here. So now the question is, what's my initial concentration of NH4 plus? At the equivalence point right now. Well, we know how many moles of it there are, right? How many moles of it are there? No. 0.025. That's the number of moles of NH3 we started with. That's the number of moles of HCl we've added. So that's the number of moles that we've converted from NH3 to NH4 plus. But the volume is different, okay? What is the total volume of our solution right now? $300 milliliters. We added 250 milliliters of HCl to a 50 milliliter container of NH3. So calculate the initial concentration of NH4 plus. It'll be 0.025 moles divided by 300 milliliters, or 0.3 liters, right? That's 25 divided by 300. Or 0.025 divided by 0.3. Okay. Cool. And we start out with none of this and none of this. Our change row is going to be minus X because the ammonium is going away, plus X here for each of these. The equilibrium will be the sum of these two rows, 0.083 minus X, X, and X. And now we can throw these into our Ka equation. We're going to. So we're going to again make the assumption that this minus X is very small and that it can go away right here. Okay? And so our Ka is going to be equal to X squared over 0.083. And so we need to solve this thing for X. So X will be equal to 0.083 multiplied by the Ka, which is 5.5 times 10 to the minus 10. And then take the square root of that, right? $6.76. So that is my X, which means that is my H3O plus concentration. How do I get pH from that? That's right. So the pH at the equivalence point is going to be equal to minus the log of 6.76 times 10 to the minus 6. And what do you get? They're about 8. Does that make sense? Weak acid, weak base, strong acid. Yeah, that makes sense. I'm sorry. All right, tell me again, 5.17? 5.17 is my pH. Well, we blew the buffer. We got past the buffered system. Okay, so now what happens if we continue? What happens if we add, instead of 250, let's say 400? Okay? So what if we add 400 milliliters of HCl? Let me write this the way I've written all the rest of them. So here the number of moles of HCl, if we say 400 milliliters, is going to be equal to, well, that number of milliliters, so 400 times 10 to the minus 3 liters, multiplied by the concentration, which is 0.1 moles of HCl per liter. And how many moles of HCl is that going to give me? Say again? 0.04. All right, so now compare this number to the number of moles that we started with of NH3, which is way up here now. So we've added definitely more acid than we had base to begin with. So we're past the equivalence point at this point. So now the calculations are the easiest, because now we just say how much extra hydroxide is there and determine our hydroxide concentration. From the hydroxide concentration, we can establish a pH, right? So that's the next step. Let's figure out how much extra hydroxide is here. So we know that, I'm sorry, how much extra HCl is here. So we know that we have 0.04 moles of this, and that it's going to react with the NH3. And it's going to react in a limiting reactant style until all of the smaller value gets used up. So how many moles of HCl will be left over? It's just going to be the 0.04 minus the 0.025. So the number of moles of HCl excess is just the 0.04 that we have minus the 0.025, which is the number of moles of NH3. So we get what, 0.015 moles of HCl. But what's the concentration of HCl? Because that's what matters, right? The pH is the log of the concentration of the acid, right? So what is our concentration of the acid? Well, we got 0.015 moles. In what volume of solution? That's right. 450 milliliters. Why? Because we started with 50 milliliters of the base, and we've added 400 milliliters of the acid. And so calculate that concentration for me. 0.015 moles divided by 0.45 liters. .033. All right, so how do we get the pH? That's right. So the pH is going to be the negative log of 0.033333 repeating, right? All right. So that's our three different cases. We've got the initial, actually, I guess four different cases. The initial, the before equivalence point, the equivalence point, and then past the equivalence point. Those are the calculations that we can make in each of the cases. All right?